Applications of discrete random variables. A game consists of rolling two standard fair cubical die. The numbers on the uppermost face are added to give a total. If the player rolls 2 or 12, they receive $20. If they roll 3 or 11, they receive $10. And if they roll 4 or 10, they receive $1. It costs $2.50 to play, and this is not returned if they win. They only receive the amount stated. Is the game fair? And if not, who stands to gain and by how much per 100 games? So to start with, the game consists of rolling two die or dice and adding the totals. So 2, 3, 4, 5, 6, 7, 3, 4, 5, 6, 7, 8, 4, 5, 6, 7, 8, 9, 5, 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, 11, and 7, 8, 9, 10, 11, 12. So we can see from there that the possible outcomes are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And there's only one way of getting a 2 out of the 36 possibilities that we can see in the table. So that's 1 out of 36, and the same is true for the 12. For a 3, though, there's 2 of those in there. So 2 out of 36, and that's the same for the 11. And for the 4, we can see 3 of those. So 3 out of 36, 3 out of 36 here as well. And if we continue, we would find that we got this, and it starts to go down again at this point. So what we're saying is that if they get a 2 or a 12, then they get $20. If they get a 3 or an 11, they get $10. And if they get 4 or a 10, then they get $1. Now we can consider ourselves to be the player. Let's let the random variable y be the amount of money that we're up. So we've paid $2.50 to play the game. If we get a 2 or a 12, we get $20. That actually means that we've gained $17.50. It's always important to read the question to see whether the house keeps your stake or whether that comes back with winnings. Usually assume it comes back with winnings. But in this case, they keep the $2.50, they just give you $20. So you end up $17.50 up, and the probability of that, 2 or 12, is 2 out of 36. We're just going to add the 1 over 36 for the 2 and the 1 over 36 for the 12. If you get the 3 or the 11, they give you $10, which means you're ahead by $7.50. And the probability of that would be 4 out of 36, since both 3 and 11 are 2 out of 36. If you get the 4 or the 10, you are down by $1.50. You gave them $2.50, and they give you $1 back. And so the probability of that is 6 out of 36. And if you don't get any of those values, you're down by $2.50 because that's what you played or paid to play the game. And so since these add up to 12 over 36, the probability of that is 24 out of 36. So that's our distribution for the outcome. So let's look at the expectation of y, which will give us the expected outcome from one play of the game. So that would be 1750 times 2 over 36 plus $7.50 times 4 over 36. Take away $1.50 times 6 over 36. Take away $2.50 times 24 over 36. So we can see that gives us negative 0.1 recurring. And over the course of 100 games, that means that we would lose $11.11. So the house, which is often what we refer to the owner of the game as, wins $11.11 per 100 games. And of course, that means that it's not fair. To be fair, the expected value would need to be 0. And then neither party has an edge. Neither party is expected to gain.